So hello everybody and welcome to our colloquium of today. It's my pleasure to introduce our speaker today, who is Australian. Initially started his studies in Australia, did his PhD at Cambridge, UK, and then of course has a very big connection to Heidelberg, to the MPIA and the ETA down here in town. CFA was also one of the places that he stopped through. He now finished to be managing director of the Argeland Institute of Astronomy. That means he's going for his next 10,000 citations. He's already gone over his 10,000 citations. And now that he has the directorship over, he can actually go for his next 10,000 ones. And now he's in Bonn, professor, and he will tell you about how some things might change completely how you think about the universe. So, welcome.
Thank you so much for this. So thank you for this very nice introduction. This title is a bit misleading. It's more about the fundamental questions of our era, as you will see in a moment. Prelude. The Standard Model of Physics is an excellent model, and with it one computes and predicts the dynamical structures which are particles and their excited states. And until now it is in excellent agreement with all our observations. So LHC and all the colliders have yielded no evidence for a violation of the Standard Model of Physics as it is mathematically known today, even though there are deep questions which are not answered, such as where all the parameters would come from. So the Standard Model of Cosmology is likewise a model in which one can compute and predict the dynamical structures, and these are galaxies and their satellite galaxies. This is what I want to talk about, and it's also part of our work in Bonn. So the Standard Model of Cosmology is based on two fundamental postulates, as you will all know. The first one is based on the idea that Einstein's field equation is valid everywhere. The second postulate is that matter is conserved. It is created in the Big Bang, and thereafter it is conserved. These are two fundamental postulates. So both of these assumptions or postulates are immediately falsified, as you will also know, because if one calculates a structure formation model based on those two postulates only, the resulting model is highly curved and structured and does not agree with the observations. So that is solved by postulating I call it a mathematical trick, and it is nothing but a mathematical trick at this stage, which is called inflation, which then solves that problem. It leads to a universe which is homogeneous and in particular flat, as far as we can see. However, if one now does a calculation of the structure formation in this type of model, again it fails, and one of the reasons it fails is because it predicts falling rotation curves of galaxies. And that is solved by postulating the existence of dark matter to make the rotation curves flat, but also there are other reasons. For example, the structure formation is too slow in that inflationary model, and to speed it up locally, one has to also use dark matter. So there are various arguments to suggest that there should be a dark matter in the universe. However, this still does not work. After all of these assumptions, postulate 1, postulate 2, plus these additional assumptions of inflation and dark matter, one finds that the universe is expanding today faster than it should, according to that model. And that is solved, again, by postulating the same mathematical trick as inflation. We call that dark energy. It's basically inflation, but it starts at a later time, basically now, and leads to this additional accelerated expansion. The problem with that is that this overall model does not conserve energy. So a physicist should have alarm bells ringing at this point. With general relativity, energy conservation is a certain issue. Nevertheless, I find this a serious issue to think about, that energy is not conserved. Now, there are other problems, and just from these assumptions and, so to speak, solutions, inflation is simply not understood.
That instead of dark energy, you can assume a cosmological constant. Do you need to say that cosmological constant does not conserve energy?
According to, if we interpret this in terms of a vacuum energy, then it does not conserve energy, yes.
Can I follow up? Even if you forget about lambda or cosmological constant, why should there be global energy conservation in VR?
This is a discussion which one can lead concerning general relativity. The question would then be, at which point would we demand energy conservation, at which point would we not demand energy conservation, right? So that's just a side comment. It's not the main issue which I'm talking about, energy conservation. So the point is that inflation is not understood. We don't have a particle physics representation of it. The existence of dark matter has not been found. Furthermore, dark energy is again not understood. Okay, so these are issues with the standard model of cosmology which simply exist. Nevertheless, it's a mathematical formulation, and in principle, like the standard model of particle physics, this model could still lead to a representation of the universe which agrees with observations. So this could still be the case, even though we do not understand all these issues. So that's the prelude of the conclusion. Conclusion of the prelude. So I was never against dark matter, but when in 2010 I started to look at the standard model of cosmology in more detail, I had to conclude, I must say, that this is a positively worst theoretical construction I have ever come across. I was completely astonished that this construction, which is based on 95% of unknown ingredients, is actually taken to be a sort of, well, a valid representation of the universe. However, that statement, which I've just made, does not constitute a falsification of the model. And it is never the reason why I would not like the model. It's just that, you know, there are issues with it which maybe from a theoretical point of view one would not like. So let us now assume that the standard model of cosmology is a valid description of the universe. And we can test it with the data of the best quality, i.e. relatively locally, where we have really nice observations. We need a test which is robust, which is logically conclusive, and does not rely on particular prescriptions of physical ingredients which one can vary nearly at will. So the idea is to construct a test which is truly robust. So assuming this model, we have this idea of how the universe evolves. We have a Big Bang, and then the structures evolve first from the dark matter, which forms into the first structures. Baryons accrete, and as that process continues, we have the first star formation, galaxies emerge, until today we see the universe as it is. So this can be calculated quite nicely in computers today. It's a large industry, and it's a very important industry, and the consequence of this, there are two consequences. The first consequence is that we have the structure merging tree. That's an inherent prediction of this model. That's how the universe has to evolve if that model is correct. So we have the first dark matter halos which coalesce, condense after the Big Bang, and they then start merging, building up ever larger dark matter halos until today we have large dark matter halos hosting Milky Way type galaxies and all the other type of galaxies which would be baryonic systems in here. So the implication of this is that the dark matter halos look as follows. This is a scale of 250 kiloparsecs. That's the center, and the dark matter halos on this scale are filled with all these substructures. These are all dark matter subhalos which are orbiting in this structure, and the Milky Way would be a galaxy in here of about this size. A large fraction, a certain fraction of these should host satellite galaxies. That's one of the big issues trying to be solved since a number of decades, is why we actually see only a small number of satellite galaxies, while there should be these thousands, if not hundreds, if not thousands of satellite galaxies. But that's not the problem I'm addressing here, because in principle, the community is saying that that problem is solved, because one can construct models of star formation where only a small fraction of these dark matter halos make satellite galaxies. However, the satellite galaxies which do form in this scenario would be surrounded by their dark matter halos. That's the important issue here. The consequence number 2 is that according to this structure formation tree, we have galaxies interact and merge. For example, here these galaxies merge, and here 2 galaxies merge to form a larger system. When this happens, because of energy and angular momentum conservation, tidal dwarf galaxies form at these instances. So here's an example: 2 galaxies merge, and because of energy and angular momentum conservation, they throw out matter in these, which is arranged these kinematically cold tidal arms. And in these tidal arms, one actually observes formation, star formation. In this case, we actually have many satellite galaxy-sized structures forming. And this is associated with the formation of a bulge. Here's another photograph of such an encounter where we have these dwarf galaxy-sized structures which are forming. Here's a movie.
Can you just go back? I may have missed this. So
yeah.
You showed in the previous picture these spiral arms. How do we know that they are not in the observational picture? The next one? Exactly.
Yeah. So this is an observed image by Weilbacher.
That's correct.
The dentist, yeah.
What do we know about the future fate of those star-forming regions?
That's a very good question, which is going to be on AstroPH, answered on AstroPH maybe tomorrow, maybe the one day after. There's a very nice work now produced by the group in Vienna, Sylvia Plöckinger, who's constructing highly resolved simulations of these sort of objects, so we know they survive, that they don't dissolve or disrupt.
But how do we know they fall into the middle?
No, they don't fall into the middle. They are in this tidal arm, and they then orbit around the host galaxy. So this, I mean, here's a movie by Wettstein and Thorsten Naab. Sorry, not this one, but here, where we have 2 galaxies interacting, and you can see that there are such tidal arms being pulled out. They condense, and we have this whole sequence of dwarf galaxies condensing these tidal arms. So we know this from theory. Here's a higher resolution movie of the same encounter. And we observe this also. We also, I will later show evidence where we actually see these sort of objects which are 1 billion years old, right? And in the computer, we know that they definitely are not destroyed within the first 1 billion years. So, thus, in the standard of cosmology, a galaxy must look as follows. We have the host galaxy with the dark matter halo. There are the dark matter satellites which have to be there, and the tidal dwarf galaxy satellites which are typically there. They don't have to be around every major galaxy, but typically a galaxy would also have these because this dark matter halo is made up of has a merging history. So these have different properties. This one forms in a dark matter halo. This one does not form in a dark matter halo. That's a fundamentally different property. That's why this is interesting. Furthermore, these are spheroidally distributed because the dark matter halo, because of its merging history and accretion history, typically is spheroidal. It's not spherical, but it's spheroidal. It can be triaxial, oblate, and the dark matter substructures follow more or less the same structure. However, these tidal dwarf galaxies are phase-space correlated because they form in tidal arms. The tidal arms remember the encounter geometry, they carry out the angular momentum, and so the tidal dwarf galaxies retain a memory of the past encounter, and typically they form these phase-space correlated distributions. So we have a clear prediction or a consequence, you can say, of any realistic model of cosmology in which galaxies interact, and that is what our universe is doing, and I call that the dual dwarf galaxy theorem. This is a strict theorem. You can really prove it out of this sort of theory. There exist type A dwarfs and type B dwarfs. And in the standard model of cosmology, the type A dwarfs have dark matter. They are dark matter dominated. That's a strict prediction. And these are distributed spheroidally. And furthermore, these, in the standard model of cosmology, these do not have dark matter because the tidal dwarf galaxies cannot accrete dark matter substantially. Furthermore, they are typically phase-space correlated. So we have a clear signature of the dynamical structures which form around galaxies, which we can now check compared to observation and test the model. So if the universe is lambda CDM, the galaxies, major galaxies must have typically these sort of satellites around them. Okay, if only one type exists, then the dual dwarf galaxy theorem is falsified. If we find that there's no evidence whatsoever for distinction, this is ruled out. That's the logically, logical inversion of this theorem. So is there any evidence, therefore, for the coexistence of two types of dwarf galaxy? That's basically now the question. It's a nice question which can be answered also quite easily. So testing the dual dwarf galaxy theorem. So here's the baryonic Tully-Fisher relation. So the mass in baryons is a function of the circular velocity. For example, here we have 10 to the 10 solar masses. So galaxies which have a mass in baryons of 10 to the 10 solar masses typically have a rotation velocity of something like 100 kilometers per second. So these are all rotational galaxies, which is a vast population of galaxies in the universe are of this type, are actually disk galaxies. Now, the important thing about this relation is, first of all, it's amazingly small scatter, but more important is that these are totally dark matter-dominated objects. These are dwarf galaxies. The rotation curve is completely dominated by the dark matter halo, also the internal regions. So these are dark matter-dominated objects. So the question is, where are the tidal dwarf galaxies, which we know are formed in this diagram? They cannot, under any circumstances, lie on the same relation because they do not have dark matter. So for the same baryonic mass, they would lie not on this relation, but they must have a smaller circular velocity by something like a factor of 10. Because typically, the mass-to-light ratio is 10 or larger, and therefore a tidal dwarf galaxy must, if the model is correct, must lie somewhere here.
Yeah. For a self-gravitating system of a given mass, I can construct them with any circular velocity I want, just depending on the size that I choose for these systems. Therefore, even without dark matter, I can make them lie anywhere on this plot where I like, just depending on the mean size of the system. So why? That is not what you just said.
So this VC is the flat part of the rotation curve. So you would have to organize the galaxy to have that baryonic mass, and that baryonic mass must give a flat rotation curve with that quantity here. And this you cannot do with a baryonic system.
So, but then it's the flatness of the rotation curve, not where they lie. Any system I can self-similarly change to rescale the velocity.
Yeah, but you have to get the flat rotation curves. You can't do that with a purely baryonic system.
So then it's the flatness of the rotation
curve,
not the value of VC.
VC is in the baryonic Tully-Fisher relation is the flatness of the rotation curve. Yeah. So you measure the rotation curve and you see where it flattens off. That's why there's some scatter here, because there's an uncertainty. Some of them have wobbles, you know. So if you look at a tidal dwarf galaxy, it should show a rise in the rotation curve, and then it should have a Keplerian decline because it's essentially only baryonic structure. So that already would be a problem, i.e. If we find a tidal dwarf galaxy which has a rising rotation curve, and if that tidal dwarf in addition lies exactly on this relation, there is a serious issue, and that's what they do. I.e. we can only interpret their rotation property if they have dark matter. So one can then now consider maybe they have dark gas, which is not seen, maybe they're accreting, they're not in dynamic equilibrium. However, it would be unlikely for three of them to lie so close to this relation. If they are in perturbed states, you'd find typically a bias to lower velocities because they don't have dark matter, and they might just lie anywhere basically, but they really accumulate just this relation. So that is already. Yeah. Yeah, yeah. Yes. I'll show images later. So these are very clearly young galaxies which have just condensed out of the tidal arm. So one could argue that they are in a perturbed state, so they show something like a strange rotation curve, but then you would expect for three of them for them to lie somewhere in this regime, but that they lie so close to this relation is a problem. This alone, one could still say maybe there are issues, so we need more data, but there's another test. So first of all, the tidal dwarf galaxies do lie on the same relation, and this can't be the case. So from this test, galaxies with dark matter are identical to galaxies without dark matter because they don't contain dark matter. So that's the conclusion from the data we have now. One would then have to show that these data are wrong if one wants to say that this is not correct. So then there's another test. We have here that these are the pressure-supported stellar systems. And here we have the projected half-light radius as a function of stellar mass. So here are star clusters. These are ultra-compact dwarf galaxies. Here are elliptical galaxies with bulges. They lie remarkably on the same relation as the ultra-compact dwarf galaxies. That's quite stunning. Not exactly sure why that should be the case, but this is at a mass scale of 10 to the 12 solar masses, and this here at a 10 to the 8 solar masses. And then here we have the dwarf elliptical galaxies. And traditionally, we think that the dwarf elliptical galaxies are in dark matter halos. So if that is the case, then they must be offset from old tidal dwarf galaxies. But we can see that the tidal dwarf galaxies actually overlie in this region. So the tidal dwarf galaxies should not be at this point because these galaxies are dark matter dominated, so they must form at a higher pressure because they're forming in a deep potential well of the dark matter halo, while these are forming without the dark matter halo, and yet they lie in the same region in this plot. So this is another argument showing that there's no difference between dark matter dominated dwarf galaxies and dwarf galaxies which do not have dark matter. I mean, we simply don't see a difference. That's the important message here. So again, TDGs coincide with dwarf elliptical dwarf spheroidal satellites, and galaxies with dark matter then are again the same as galaxies without dark matter, i.e. there's simply no visible distinction between these two in terms of their morphology and kinematics, because the mass of these objects are determined by studying the motions of the stars of these objects. Okay, so there's no difference. Therefore, the dual dwarf galaxy theorem, so we've seen that there's only one type of dwarf galaxy. The dual dwarf galaxy theorem is falsified, and therefore the logical conclusion is that the smog is ruled out. Okay, that has been shown, and that's the end.
Which kind of rotation force do these tidal dwarf galaxies have?
So right. So I can, of course, this is a strong conclusion because it basically means everything is ruled out, right? So, you know, is this really a valid conclusion? We want to be sure that we have to discard Einstein's field equation, maybe. We have to discard the whole concept of dark matter. Dark matter can't be there. Dark energy is not there. Basically we start anew in developing a cosmological model. So is that conclusion really based on the dual dwarf galaxy theorem completely solid? So we need consistency checks. We really want to make sure this is a solid conclusion. So the consistency checks are actually what is, I think, interesting here. So we've seen here that we have the dual dwarf galaxy theorem, and these have spheroidal distribution, and these have a phase-space correlated structure. So we can use that as a consistency check. If our conclusion was correct that this is ruled out, then that conclusion has to be carried just by the spatial arrangement of the galaxies around their hosts. So consistency check one is that if the Milky Way satellites are tidal dwarf galaxies without dark matter, then they ought to be in a phase-space correlated distribution, and we already know that they are, right? So this is the Milky Way. There's about 400 kiloparsecs on each side, and we can see that there are the ultra-faint dwarf satellites, the dwarf spheroidal satellites, young haloglobular clusters. They all follow the same structure, this highly anisotropic distribution around the Milky Way, as well as a large fraction of the known streams also aligned with the structure, which means we have an object, some structure which goes from something like within 10 kiloparsecs out to 250 kiloparsecs, and every subcomponent we look at, if you look at the dwarf spheroidal satellites, with the classical satellites, the ultra-faint satellites, if you look at them separately, and we fit as a linear structure or see how they are distributed, we get the same result in every single case. These. Oh, good question. It must be.
That lies in a very different place.
That, yes, sure.
And it's by far the biggest stream of them all.
Right, that is actually at right angles, but it's very close in, right? It's somewhere in here. Yeah. So that's the overall structure. We see not every stream actually aligns. These streams are magnified by a factor of 10, so actually they are a factor of 10 further in here. This is just to show how they orient themselves. But even without the streams, you can see that the young haloglobular clusters, ultra-faint dwarfs and dwarf spheroidals form the same overall structure. If we do a statistical test on these subcomponents, they come from the same parent distribution. And they are completely inconsistent with stemming from something which is more spheroidal, i.e. which actually comes from a cosmological structure formation. So therefore, if the Milky Way satellites are TDGs, they ought to be in phase space squared distribution, and yes, they are. So this is a consistency check. This alone would not be against the standard model of cosmology as an argument. However, it's a consistency check on the conclusion that the dual dwarf galaxy theorem is falsified in the SMOC. So
could this not just be a random effect on primordial dwarfs? We are sitting in a filament, in a slab, which has an orientation, of course.
Yes. No, that doesn't work. So we've tested this, the available cosmological models, Aquarius, some other calculations on the anisotropy, which one can find around host galaxies. Marcel Pawlowski has done this test. And the hypothesis that the structure could be derived from, say, filamentary accretion is completely excluded. Yeah. And this is published.
Look at the anisotropy of the dark matter satellites that are likely to host the galaxy. You do that.
Yes, yes. So in the Aquarius simulation, we basically have the dark matter substructures, and that never leads to these high anisotropies. You can then start thinking that your visible satellites are you have to sub-select, right? And but then. Well, you can just say, let's have a dark matter halo with the dark matter substructures, and you just paint those which are in a disk to be satellites. And for some unknown reason, nature makes just those light up, right? But that is not a solution which I favor, because it has no physics in it. So, but that's, as I was saying, that is only a consistency check. The exclusion of the SMOC is not based only on the anisotropy. So here's another test. If the Milky Way satellites are dark matter-dominated subhalos, then they have to have fallen in recently in order to be arranged in this large polar structure. And this is a paper by Deason et al., who've clearly shown that to explain the structure as the satellites being dark matter-dominated, they must have fallen in recently to still sustain the structure, otherwise it disappears because of phase mixing and so on. Then at the same year, another group, this Australian group, has shown that if they are dark matter subhalos, then they have to have fallen in a long time ago in order for them to have lost their gas. Okay, this is inconsistent. It's the same model, but it's totally inconsistent. They don't cite each other. So this is a logical inconsistency in the standard model of cosmology. Yeah. No, sorry, I don't buy that solution. I'm dealing with baryonic physics as an astronomer every day, and yeah, that's not an explanation for this, sorry.
Well, if you don't know baryonic physics, you don't know what the physics is correct.
Well, none of them are correct because the model isn't correct. Right? So, what's the origin of the vast polar structure? Here's what I think is the origin. We have interacting galaxies. This is a real photo. This is a galaxy encounter model. Galaxies then separate. Here is a tidal arm which wraps around this galaxy. Here's a model of such a structure. And here's now then when they separate, we form these tidal arms, and they form, as you know, in observation, these dwarf galaxy-sized tidal dwarf galaxies. And in the model, of course, one can then, from such an encounter, produce such an anisotropy readily. There's simply no major magic involved, also no real fine-tuning of the parameters. This just comes out, and these structures are stable at right angles of the host galaxy. So there's another model by Fouquet, Hammer et al., published, which is also another elegant explanation which one can take seriously, where the satellites of the Milky Way are tidal dwarf galaxies. So the Milky Way satellite galaxy system is thus naturally explained as having been born in a past encounter between the young Milky Way and another young galaxy. And this happened about 10, maybe 11 billion years ago.
That young galaxies,
we don't know. We don't know. It could be Andromeda, yes. If it was Andromeda, so...
but is there any other indication of that except for this part? For from anything else, from stellar structure?
Well, as I was, yes, so they all have so the satellite galaxies have stellar populations which have ages which go back, as far as one can resolve 10, 11, 12 billion years. One can't really distinguish. 10, 11, 12 billion years is okay. And that's what is consistent with this model. Well, we can't go back and see a movie of this, right? So we can only deduce by observing the phase space structure.
So this is really the indication of it, because otherwise you have to take stellar ages.
So the other evidence, which I didn't mention, is that this whole structure, Milky Way, and this whole structure is actually rotating. Right? Basically every satellite for which we have proper motions, apart from one, but they're all going in the same direction. And so one of them is going the other direction, the same structure. And that is a telltale sign, because actually, if you look at such an encounter here, we find that as this tidal arm wraps around this host, first one produces satellites on this orbit, and as the tidal arm wraps around and then moves past this structure, one forms satellites on that orbit. And so the ratio between the satellites on in one direction with respect to the satellites in the other direction gives us a nice constraint on the actual encounter which happened 11 billion years ago. That's really a remarkable feature.
Is it true that in all those encounters, the two galaxies at the end will coalesce together?
No.
In those kind of encounters, I think yes.
The evidence, we can discuss the evidence for merging later, but the word merging is being used far too often. And under which evidence do we have, when you see galaxies interacting, which evidence do we have that they are merging?
Well, if you use a simple canonical fiction argument or random simulation, the galaxies are going to merge.
In which framework?
The Newton plus theorem.
All right, but this is excluded. Okay, so this work has been done by Pawlowski, Dabringhausen, and in Vienna by Sylvia Plöckinger, whose paper will be on AstroPH within a few days. For the first time, the very detailed simulation of tidal dwarf galaxies will be presented. I think it's a breakthrough research paper. So here's now consistency check number 2. So other extragalactic phase space clouded distribution of satellite galaxies. So the idea is the Milky Way galaxy unique on extreme outflow? We could always argue the Milky Way is completely unique. Is there any evidence for such phase space clouded structures around other galaxies? Is that common? So if the universe is built up through this, so if galaxies are interacting commonly in a real universe, these phase space clouded structures should not be unique, only limited to the Milky Way. And yes, of course, they are not unique. In fact, they are very common. So here's one case. This is this galaxy NGC 5291, which has produced this tremendously large tidal structure. And in this tidal structure are these very young galaxies which have just formed. And these are the tidal dwarf galaxies which appeared in the previous plot. So astronomers in France have... So Frédéric Bourdon et al. Have measured the rotation curves of these dwarf galaxies, and from that we know that they lie too close, or basically on the baryonic to the Fisher relation. And this is a computer model, so we can actually reproduce this morphology very nicely, and even tidal dwarf galaxies form in the computer model, very similar to what is observed, as you can see.
Which framework is the simulation done?
This is in the standard framework. Exactly. Yeah, very good. Very good point. Precisely, yes. That's correct, yes. Which is why the question is whether this actually is a merger, right? But in the, the idea is that we are still working, in this case, working in the standard framework. We are testing the standard framework, so we are doing the calculations in the standard framework to compare with the observations. In that sense, this is consistent. However, then in this test, the test fails, so this framework is ruled out because these tidal dwarfs do not have the rotation curves which are observed. So we have to then start thinking how to change the standard framework to account, yes, for this morphology, but also for the rotation curves. And we maybe will get to this towards the end of the talk. So here's another case. This is the Tadpole galaxy, where we see the beautiful tidal dwarf galaxies forming in this tidal tail, again in this very nicely correlated structure. And then here we have a 2 to 3 billion year old post-merger, as it's called. Maybe this is a merger, by Duc et al. again from France, where they found this tidal stream and these dwarf spheroids, and these are completely normal dwarf spheroidal galaxies in this linear structure associated with the tidal arm. So these are old or intermediate age tidal dwarf galaxies for them to be arranged in this sort of structure, as also discussed in that paper. And then we have here Andromeda galaxy with all its satellites. That's a complicated system. It's a very rich system, not only its globular clusters, but also its satellites population. And it has already been noted some time ago that there's a large fraction of satellites which are in this linear structure here. And there's this paper by Ibata et al., which has caused some waves, where they found that this is an extremely thin structure of satellite galaxies, which is rotating around Andromeda. They're all going in the same direction around Andromeda, because they also know the radial velocities through spectroscopic analysis. So this is 50% of the satellites are in a highly, really thin structure moving around Andromeda.
But 12 galaxies are also almost perpendicular to this one.
Well, if you look closely, there's another linear structure which is around here. Yes. Yeah. Yeah, but it's not an isotropic distribution. Yeah. So, by the way, if the Milky Way has such a structure of satellites, we wouldn't see it because it's in the disk of the Andromeda, of the Milky Way. So, and here's another very nice case by David Martinez Delgado, NGC XXXX, where we have this galaxy here, they're interacting, and you see this nice structure here, where with the GALEX imaging, we see star formation, and this is another very nice linear structure of dwarf galaxies forming this phase-space coordinate structure. So speak to David, who has the information, and therefore we can say that, you know, is the Milky Way galaxy unique or an extreme outlier? No, it is not an extreme outlier. Yeah. And so remember, this two-dwarf galaxy theorem, this is, I think, completely ruled out. I just don't see any possibility to sustain that model. Now, I'm not saying that lightheartedly, because I know this is not a comfortable conclusion, but, you know, as a scientist, that's what I do, whatever the consequences might be. So, therefore, the SMOC is ruled out. And still one wants to ask, if this falsification is true, with all the consistency checks, then the standard model of cosmology, when applied to the data, must show other and general discrepancies of the data. Now, I have also been in talks where the speaker has been telling the audience that the standard model of cosmology is in excellent agreement with the data, right? So where is this agreement? Well, I've invented this theory confidence graph, where what we are seeing here is a time axis in which various hypotheses are put up. And then here's the log confidence. So the idea is that we put up a hypothesis. In this case, it's general relativity is valid on all scales, and BB nucleus and thesis, i.e. Conservation of matter, is the second one. That's our fundamental hypothesis. Each time the model fails some test, the confidence goes down by some step, right? And typically, since we multiply probabilities, this is a log scale, right? So
what happens if the model makes an outrageous prediction that turns out to be true? Does it go back up?
Then you can say you gain confidence. You could do that, yeah, in principle.
That's never happened.
No, no, the way, I mean, this is going back to, I think it was Popper, right, who suggested the way to test hypotheses is you falsify them rather than affirm, right? So so falsifications are what count, not affirmations. So in this case, the model is excluded because of its highly curved substructured model. So we have to invent inflation. So that's, you go down in confidence because you have to put in another assumption. Okay, the model is again fails observations because of the structure formation then isn't fast enough and rotation curves are flat. You have to invent dark matter. You go down because another assumption is to be put in. And then you make other predictions like the angular momentum problem in disk galaxy formation, the Cusp-Core problem. Each time you go down because the model doesn't actually yield what the observations are telling us. Here is another major step. These are in black because these are associated with new physical ideas. Here we have the failure because of the universe seems to be expanding too rapidly, so we invent dark energy. Again, we go down because we have to put in another hypothesis, and so on. Missing satellites problem, the downsizing problem, the substructure, the anisotropy problem of the satellite distributions, the tidal dwarf galaxies being on the Baryonic-Tully-Fisher relation, essentially, and so on. Another fairly major problem is this bulged disk galaxies. There are a large fraction of the disk galaxies do not have a bulge. That's difficult to explain because the model is fundamentally collisional, i.e. we should be making bulges readily in these galaxies. And another really major problem is this missing dark matter, which appeared fairly recently, where Karachentsev has just added up all the galaxies in the 100 megaparsec volume around the, I think it was 100 megaparsec volume around the Milky Way, and found that a factor of 3 to 4 of matter is missing, i.e. we are living in a hole, basically. Yeah? And that's, at that level, on that scale, the Standard model of cosmology is only allowed to fluctuate by about 10% in density, but according to the observations, it's a much larger fluctuation. So that alone is a major problem for the model. And this is, so neither the observed real galaxies nor the nearby 50 megaparsec universe, it was a volume with radius of 50 megaparsec, which Karachentsev looked at, show properties typical of dark matter. I mean, that's just the way it is. The model is not a good representation of the observed universe. Cold, warm dark matter particles therefore cannot exist, and I'm very confident about this. 5 years ago, I would not have made that statement. Said again? Yeah. Yes. No. Right. You could maybe say that possibly. Karachentsev argues that it's the dark matter which is missing. Yeah.
But he didn't find no dark matter. Some dark matter is missing, so there is still some dark matter.
Well, what he did is he counted up all the baryonic structures seen by the universe in galaxies, and then just assumed that each one has a dark matter halo, and then found that the dark matter mass in that volume is a factor of 3 to 4 too small compared to what it should be in the standard model. So yes, maybe you could argue against inflation with that argument, possibly, by saying there's sort of, it does lead to some sort of inhomogeneities.
But if you remove inflation, then that's an argument against standard model.
Yes, yes. So, yeah.
Another complaint on your graph on the page before. The bullet cluster, not
Can I maybe just suggest to let the speaker finish and have the questions after? Thank you.
But this is an important point, but it's not. It is a step down.
You tell us why.
Because the high velocities, right? You have similar mass clusters to have the shock structure. You need a particle velocity, and to get those clusters on that mass scale to go through each other, that velocity is seriously unlikely in the STEM model. Well, that's what I'm not talking about opinions. I'm talking about what is in the literature. I'm not interested in opinions, so I want to see stuff written down, published.
Andrea, 5 minutes. Andrea Macchio, 5 minutes. Time out.
So, okay, so the bullet cluster is not even very relevant in this point, however you might argue about it, but I'm confident that cold or warm dark matter particles therefore cannot exist. Yeah, that's really, I'm very confident about the statements, and the smog cannot be the correct description of the universe, and which impact does this have for fundamental physics? Now, I think comes really the interesting stuff. What does this actually imply? What does this imply for understanding reality if we've ruled out basically our current understandings? So, do the data on galaxy scales contain clues? And they contain very interesting clues. So here we have the mass discrepancy correlation with acceleration, also called the Stacy-Magog correlation or plot. So we have a galaxy, a circular orbit, and we observe the velocity of matter at that radius going, with this velocity v, that's the circular velocity observed, and this is the velocity the matter should have if there were no dark matter. just given by the baryonic matter. And so we can calculate the ratio V over VB squared, which is a measure of the amount of mass within the radius, which is missing. And this is the data. So each of these sequences is one galaxy. You can see this galaxy has this sort of rotation curve in this plot, where here is the acceleration. This is the radius in meters, and we do not see any particular correlation. But if we now plot the same data, this is what McGough did, as a function of acceleration, we get this remarkable correlation. Yeah. You see there are many different galaxies here with different rotation curves, but in mass discrepancy acceleration scale plot, there is this amazing correlation which appears. And this is with the solar system scale, where you can see that the solar system is deep in the Newtonian regime. And here, when we go to an acceleration 5 orders of magnitude smaller than the outer planet, we see a violation of the Newtonian regime. And the galaxies are in this regime. So what is this regime? What does that mean? The dark matter particles can't really make this because they don't care about the acceleration. So let's consider space-time scale invariance. This is what Milgrom 2009 suggested. We looked at this again recently. Currently, we are looking at this even more. We have the time-space vector, and if you just imagine you have this transformation, you just say lambda is a number, 3. You just scale your space-time scale vector by some scalar. Under that transformation, the Newtonian gravitation acceleration scales is gm over r squared, i.e., under this transformation, the acceleration scales is lambda to the minus 1 gn because of this r squared. Yeah? But the kinematical acceleration, g scales as lambda to the minus 1g, because you've got d, so you've got x dot, which is dx on dt, the lambdas cancel, but you have this dt down here, and therefore it scales as lambda minus 1. They don't scale the same. If we now demand, and this is just a hypothesis, demand the kinematical and gravitational acceleration to scale the same way, we have to force our gravitational acceleration to scale with the Newtonian acceleration square root of the Newtonian acceleration. I.e. g must scale as gn square root of that, and since in order to have the same units here, we have to introduce a constant which has the units of acceleration. We can actually, and this is what we are doing now, link this A0 to the Hubble constant, which is quite remarkable. But let's just introduce this constant here, i.e. from this equation, we just say that we only have this constant, so we say an equal here. We have g squared is equal to a naught gn, i.e. a squared is a naught gn. So the a naught appears simply because of this demand, no other reason. Currently it's just a hypothesis. So the Newtonian acceleration takes this value, where this is the actual acceleration and a0 is our new constant. So with this space-time scale invariance, as we call it, this is called, we can then derive, so this equation here is the same as this equation, where we've now replaced gn by the actual gn, the Newtonian acceleration. And since we have centrifugal acceleration being centripetal acceleration, looking at orbits which are on circular orbits, one finds then that from this, directly the Tully-Fisher relation emerges. Yeah, and that's what nature does. Whatever it means, but that's actually what comes out of it. And of course, you get flat rotation curves, so rotation curves fundamentally have to be flat. So now look at the baryonic Tully-Fisher relation. This is again a plot from Fermi and McGough, going down to, as you can see now, is a mass scale of a few times 10 to the 6 solar masses, up to 10 to the nearly 10 to the 12 solar masses. Very amazing correlation. This little galaxy here has a rotation velocity of 50 kilometers per second. There's a mass of a globular cluster, and it lies exactly on the baryonic Tully-Fisher relation. This is the rotation curve of this dwarf galaxy. It's really remarkable. What we also see is that there's no kink at this mass scale of 10 to the 10 solar masses, because some models of galaxy formation suggest that there's hot accretion of gas in this range, cold accretion in the lower mass halos. But there's no structure at all suggesting that the accretion of baryons into dark matter halos differs in any of these galaxies, i.e. leads to structure. There's one simple law which must be a fundamental law of nature coming out of this. And so, again, here are the tidal dwarf galaxies lying on this relation, where now today we actually have data for even less massive disk galaxies, which also beautifully lie on this correlation. So TDGs are purely baryonic objects. So why are they so similar to other galaxies? They are similar because nature follows this scale invariant dynamics, and then of course they have to be on this relation.
I'm sorry, the TDGs are in the model mentioned, right? They should.
I don't want to mention that word in this talk. I'm talking about scale.
If they are, and you're predicting a flat rotational curve, and you said that it drops.
So I'm saying if we assume space-time scale invariance dynamics, then nature has to behave exactly the way it is behaving. You will see by the cited literature what I'm referring to, right? So again, consider the space-time scale invariance. You've seen this already. This is very simple arithmetics. So we can then derive this little relation here between the mass discrepancy and acceleration. So that again follows directly from this relation here. And this is where the data lies. So this is the mass discrepancy acceleration correlation I showed before, and this is space-time scale invariance. It is exactly spot on for one single value of A0, which leads to a Hubble constant of about 73, what was the units, kilometers per second per megaparsec, I think. Okay, so I refer to this Milgromian dynamics, getting a bit closer to what you said, right? There is a relation, you can derive Milgromian dynamics from the processes in the vacuum. This is most remarkable. This is really extraordinary. This is what he's done in one of his papers. It's cited somewhere here, where we discussed in Appendix A. This might be an easier to understand discussion, but in his one of the papers, I can't find the reference here, so Milgrom 2000 something, I think, he shows that if you are, so observers experiencing a very small acceleration would thus see a Unruh radiation with a low temperature close to the Gibbons-Hawkins one. So Unruh comes from the vacuum. If you accelerate, the vacuum is blue shifted, exerts a pressure. The Gibbons-Hawkins radiation comes from the horizon and is basically the same in all directions. So this means that the inertial resistance defined by the difference between the two temperatures would be smaller than in Newtonian dynamics, where you're in a strong acceleration regime, and thus the corresponding acceleration would be larger. And this ansatz gives precisely by the formula given written down by Milgrom in 1983, i.e. this is the transition function, which then comes from process in the vacuum. This link of that dynamics to the vacuum is, I think, really remarkable. So scale invariant Milgromian dynamics is, I think, the current best bet. One explains rotation curves precisely, i.e. these kinks very nicely. In lambda CDM is difficult because the dark matter halo is more or less spherical, and really it's difficult to account for these kinks. What is also important is this issue here, where in this paper, Angus and Diaferi has shown that in this sort of model, i.e. Milgromian dynamics cosmological model, one can actually account for the cosmic microwave fluctuations as well as the lambda CDM model. What I take this to mean is that the concordance cosmological model, the standard model, does not uniquely account for the CMB, morphological structure. So this only shows, it doesn't prove any particular model. Consistency with the CMB does not prove any particular model. This exercise proves the one thing, and that is we do not have a unique model for the CMB. We have another model which accounts for it equally well, and that is not the standard model of cosmology, and it does not contain cold or warm dark matter. So the falsification of the smog, it has become, I think, irrelevant to ask whether any set of data actually fit the smog. It's like today debating whether the geocentric model is still fitted by some data, right? So the conclusions are that the dual dwarf galaxy theorem is violated by the real universe, and thus the standard model of cosmology is falsified. That dynamically relevant dark matter cannot exist in galaxies. The search for it will be fruitless. Effective dynamics is scale invariant, Milgromian, i.e. dark matter must be mathematically equivalent to Milgromian dynamics. If you'd still desperately want to think of dark matter particles, you have to somehow make it to basically be Milgromian dynamics. That's the only option you have. So this is ruled out, and that's the new structure formation tree, where we have only baryonic structures which make tidal dwarf galaxies. And with that, I want to finish. Thank you.
I have never seen such a like the colloquium. I'm very impressed with everybody, and especially Mrs. Speaker for being so patient with us. As always, students first, if you have any questions. So, do any of the students in the audience have any questions? Yeah, go ahead.
First, called inflation and mathematical tricks, and a second, you call it a reason to lose confidence. And I wonder why you do so, because it provides a nice mechanism for seeing the cosmic structure formation.
Could you repeat that again, please?
I wonder why you call inflation a reason to lose confidence when it sees cosmic structure formation so nicely.
As I was saying, so the philosophy of testing scientific theories is as follows. You set up a hypothesis. The hypothesis in this case is that Einstein's field equation is valid and all matter is conserved. And with that hypothesis, one does not agree, the predicted or the calculated structures do not agree with the observed structures, which means you now have to add additional hypotheses. And inflation is an additional hypothesis. It does not come, the idea of inflation does not come from some fundamental physical ideas, like from the standard of particle physics, but it's an assumption made only to fit that model with the data, and therefore it's an additional and augmentary hypothesis unique for solving that technical problem. And so one loses confidence. One can save the situation by saying that, yes, I've lost confidence, but this means there's a prediction like the inflation, which may be associated with other phenomena like particles or something, and if those particles are found and verified, then that loss of confidence becomes a big triumph. Yeah, but this has not happened so far.
So all Milky Way asteroids do have an old stellar population, as you said, but many of them, in fact most of them, do have later epochs of star formation. So in your tidal dwarf formation picture, what triggers or sustains star formation at these later epochs, billions of years after the initial gas accretion event for these systems?
Yes. So a tidal dwarf galaxy can have multiple different tidal dwarf galaxy can have different types of apparent star formation histories, right? So if you can imagine the following scenario, you have a major disk galaxy which is interacting with another galaxy, and the tidal dwarfs which form contain population of stars which already existed in the galaxy. So when they plus a burst of star formation or addition of new stars formed in that formation of the tidal dwarf galaxy. Right? Because the part of the disk is pulled out in a thin kinematic tail which contains gas and old stars that then collapses to form a new tidal dwarf. So there's probably some little burst of star formation at that time, and it contains the older stars from the previous galaxy.
If you have something, say, like Carina, which has 3 distinct bursts, like how do you, like you say the old burst comes from some host galaxy, then you get a second burst from what? I mean, like, I'm just trying to understand. I mean, there's a wide diversity in these star formation histories, and I just don't understand how this mechanism can produce all of them, I guess.
This is a very important question which is now being addressed. Yes, it's very relevant. So the question is, can one account for complicated star formation histories in tidal dwarf galaxies? So far, what the calculations from Vienna have been showing, yes. Right? So if you have a tidal dwarf galaxy, which you start off as a cloud of gas in the potential of a host galaxy, this will collapse, form a little rotating disk galaxy, there will be a burst of star formation, and and this dwarf galaxy can then either sustain a self-regulated star formation history, which we see in the computer. This will be coming out in AstroPH pretty soon, in a few days. What can also then happen is that if this now little dwarf galaxy, which is rotating and has a star formation activity, which is self-regulated because it's retreating gas from the tidal, from its surroundings, is now in orbit in the host galaxy. It's probably not going to be a circular orbit, it's going to be some eccentric orbit. So as it goes in, closer into the potential of the host galaxy, it's going to be squeezed, tidally perturbed, which channels gas onto radial orbits in the tidal dwarf, and there will be another burst of star formation. And this is known already from the dark matter simulations by Lutz Meyer from Zurich. Those models apply equally to tidal dwarf galaxies because in the real universe, the scalar variant dynamics case, growing dynamics, each tidal dwarf galaxy has a dark matter halo around it, but it's a phantom dark matter halo. It's not a real dark matter halo, i.e. it behaves basically very similarly, not identically, but very similarly to the calculation which exists with dark matter. And so what you see in the literature based on dwarf galaxies with dark matter halos applies to the real universe with a slight modification that the phantom dark matter halo now becomes a dynamic property of the galaxy. That means as the galaxy moves in, the dark matter halo is truncated because of this additional effect in this dynamics, which is referred to as the external field effect. And as it moves out, the dark matter halo expands again. Nevertheless, it basically has an effect of dark matter halo. So you can have bursts of star formation related to the orbit of the satellite galaxy. You can also lose all your gas in the tidal dwarf galaxy because of random pressure stripping, in which case you will only have either the population from the previous older galaxy or the population which formed when the tidal dwarf galaxy formed, and then the gas was stripped. So you can basically have all sorts of star formation histories, and I don't see any problem with the observed star formation histories in our satellite galaxies. However, it's a major research field which is now starting to really address exactly this.
Sorry, we're still on students. Yes.
So can Carina be explained in terms of a tidal dwarf galaxy?
So, in your cosmological model, you will also have a Big Bang, and how old is the universe?
It's not my cosmological model, right? I've been referring to this particular work by Angus and Diaferio, which I think is groundbreaking, and that model is still very conservative. It's based on an Andromeda dynamics universe without colloquium of dark matter, but otherwise it's basically the same. It has the same age, very similar expansion history, basically the same expansion history. They still need dark energy in that particular model. The difference is that they don't have dark matter, so the galaxy rotation curves, barometric relation is accounted for naturally, as well as the satellite galaxies would have to be mostly tidal dwarf galaxies, plus the prediction of that model is that you need dark matter, but it has to be hot dark matter. And in fact, they make the statement that in order to be consistent with the lensing galaxy clustered in that framework, the dark matter particles have to have a mass of about 11 electron volts. So that's a prediction from their work, but I would not say that that is the real universe. It just shows that the CMB can be explained in a completely different framework, but this framework is not completely radically different. It just doesn't contain dark matter, and it's Lagrangian dynamics.
Okay, so last question by a student, and then it's open for everybody if you can go. Okay.
My question is to gravitational lensing. So, I mean, initially, a lot of the dark matter, the theory came from seeing that there's more mass when we look at gravitational lenses. So, how does your Milky dynamic explain?
Well, I'm not an expert on lensing, right? But there are very few people who have actually done lensing in Milky dynamics, so you need a special general relativistic formation of Milky dynamics, like Bekenstein, and those few experts who can do the calculations, do the calculations, and of course you get a result in terms of the amount of matter. I can't actually currently recall exactly what the result is. If I remember. So in Andromeda dynamics, the mass discrepancy, the sense of the additional matter you have to put in, is very much limited. It's only about a factor of 2 which is missing, if at all. And so that is consistent with also the motion of the galaxies. This is my recollection of the state of the affair. there is no mismatch between the lensing in Brownian dynamics, i.e. the relative information of it, and the data, except that the mass distribution derived is of course different, because the underlying theory is different.
Okay, now the paper is open. Yes.
How do you describe the fact that the Atlantis again reproduces very nicely the classical galaxies, and also the classical individual galaxies,
that it reproduces the clusters of the standard model cosmology produces the clusters of galaxies very nicely. Well, as I was saying, the fundamental philosophy in science is to falsify. So agreement, it's nice, but it doesn't really. It maybe enhances. So I wasn't finished. So I was just saying that even if you have agreement, it doesn't actually. It's nice, it maybe enhances one's confidence somewhat, but it's not something we can count. It's a falsification, which is important. However, my recollection of the issue with galaxy clusters in this term of cosmology is that it's a problem, because very massive clusters are observed at a very high redshift, where there's an issue of actually assembling such structures in such a short time. Right? So there are some papers which have been claiming that there are really very massive galaxy clusters at a very high redshift. I don't remember the numbers, but this was taken to be a stress with the model. So that's one answer. And the other, you said that the galaxy population is nicely consistent with the observations. That's a good one, yes. So here's my counter question. How do you measure the correlation function in the model? I mean, not mathematically in detail, just what traces do you use? Yeah, very good, wonderful. Okay, so, but the model, the structure formation is based on what?
These galaxies live in dark matter halos.
Dark matter halos. Right, so how do you paint your dark matter halos with galaxies?
With the bionic process that you think are correct.
That you think that are correct, right. However, there is something which you can adjust, right? You don't measure the dark matter's correlation function, you measure the galaxies you put into your dark matter halos, possibly in order to improve the fit. So
your colleague Peter Schneider actually by weak lensing does measure the dark matter correlation function.
Does not.
He does.
He does.
Yeah, it's sheer correlation functions. I mean, I know it's a floor down from you, but
well, the uncertainties are quite large. That's on that topic. So I wouldn't say that agreement is really binding or proving the model.
Do you have any other questions? I assume we might. Okay, and that is now out.
Just on a philosophy report, you mentioned at the beginning the southern model particle physics. And we know the southern model particle physics is wrong because neutrinos do have masses. But nobody is thinking of throwing it in the garbage. People are trying to extend it, improve it. And I think it's the same argument for quantum matter. Quantum matter has a lot of success that you are likely to ignore. You just mentioned that the success is not something you care about. Throwing the model so successful away because it has some flows on small scales, I think it's the wrong philosophy, because maybe one can try to adjust the model. Because most of the things you mentioned on this scale of the confidence, they were all come from numerical simulations. And if there's a thing which is by definition approximate, is a numerical simulation. So improving our understanding of the physical variance and the relation to dark matter, and improving our capability to put those things in a computer has solved most of the things you mentioned there. So while I accept there are some issues in most cases, and I think this alignment of satellite is a striking one, and I'm with you with that, I don't think that throwing away the model that is so successful should be the right philosophy.
What I've tried to tell you is that actually the model is completely unsuccessful. So I think we are not on the same level here. I'm an astronomer and I've been looking at these data now for a long time, and I simply don't see the agreement. So it's basically completely false. Every single prediction has been wrong. The two-point correlation function is constructed after populating dark matter halos with galaxies. But here's one question to you. If it's such a wonderful model, so give me a simulation box, say 50 megaparsec, 10 megaparsec large, Tell me, in terms of a self-consistent calculation, including baronic physics, the current standard prescription as Governato et al. Or Brooks, who claim they can form disk galaxies, put that into the model and then tell me what population of galaxies you actually get in that model. I can guarantee you that the dominant population of galaxies you will get are spheroidal, i.e. If there are, I guarantee that is the case.
That's wrong.
Well, I think we stand that it's wrong because
It's Volker in the audience. No, it's someone from
because the disk galaxies which you want to form in your model, you have to select the dark matter halos to not have a significant merger history. Well, this is documented in the literature.
That was
Pavel,
I
can say that.
Oh, Volker, thanks.
Just completed a simulation with 75 megaparsec box, a very large model. It's a standard cosmology with sophisticated baronic physics. So this is basically like a Millennium 2 simulation with baronic physics, and you do get the correct morphological mix of galaxies, the correct sizes, the correct clustering patterns. All of this predicted as a function of colors, as a function of stellar mass, you name it. I mean, this is just, these are predictions that are not tuned from the beginning.
Okay,
and I challenge you, I can't see possibly how Milky-Way dynamics model, which nobody has, of course, carried out this calculation, but I think I invite you to apply your own standards of falsification to Milky-Way dynamics, because I can bet you that you find on so many ends disagreements with data that go way beyond the little theoretical conjecture to be raised here about tidal dwarf galaxies, whose existence, by the way, is not undisputed, right? Whether this even exists, this channel that you claim exists, that you make a tidal dwarf.
Well, I completely disagree with what you said. I look forward to the paper which you're claiming. You're saying that in your simulation box you produce the observed population of galaxies. That's a strong claim. We look forward to seeing this and testing if the feedback processes you actually put in there are what we observe in the local universe. That's a very nice exercise, which of course we will be doing.
We were talking about the morphology.
And
now you're saying that I'm not using the right physics. This is another aspect we can discuss, right? Whether the feedback you require is correct. But I think it's a totally different story. We can disprove you what you said earlier, that we would make primarily spheroidal galaxies. We do get disk-dominated systems. We partially have even too many of those now.
Well, as I say, I'm looking forward to seeing that paper, and we will look at it. And concerning the dwarf galaxy theorem, the challenge is to show that it is not violating the universe.
I think with this really inspiring new work by all the people coming out, we should thank our speaker again and thank you guys for really